All right, let's say we have a problem like the following. So we've been asked to plot a function f of x, which is e to the x over 5 times this combination of sine and cosine. And we've been told to plot it from x equal to 0 to x equal to 2 pi in steps of 0.001. Okay? Now to understand how to do this, we got to look at this a couple of different ways. Essentially what we have is some function, e to the x over 5, times some other function in here. All right, and that can be a little bit tricky for you to perform in MATLAB. So to understand this, we need to review a little bit about how MATLAB functions. Now, as we've talked about, right, if we have a function f of x, the way you've learned up till now is that x is a continuous variable, meaning x can take any value, any real number value. Okay, that's very difficult to create in a computer, right? If I wanted to plot this function f of x from 0 to 2 pi, and I wanted to plot it at every real number x between 0 and 2 pi, then this thing, all right, this function, which would be created somewhere in memory, would be impossible to store if we tried to store it at every possible number x in that range. Okay, so what we have to do is we need to choose the points at which we do it. All right, and that's why we've been told to plot from x equal to 0 to x equal to 2 pi in steps of 0.001. All right, we're only going to plot at certain points. Obviously, the steps could be a lot smaller. Okay, but if I made them smaller, I would just end up storing a whole lot of data. I could make them bigger steps, right? I could do something like 0.1, but then potentially at some point my steps would become so big that the function may not look right when I look at it. Okay, there's an art to maybe choosing, what that step is, not making it too small, but also not making it too big. All right, so let's think about this then. Essentially what we do is we create the points x at which we want to see f of x. And so we think of it like this. In this case, I create a row vector which has a starting point and an ending point. Okay, so we have x. So I begin at x start. I increase in increments of x step all the way to x end. So for what I've been told here, if I want to plot from 0 to 2 pi in steps of 0.01, I say this becomes 0 in steps of 0.001 up to 2. In MATLAB, I would say 2 times pi. Okay, like that. So I define that x vector. And then at the output, what I'm going to basically get from this, so I viewed this as sort of a block diagram that says I put this input x in and I evaluate f of x at those points. So basically, if I created a vector f, that vector would have f of 0, f of 0.001, f of 0.002, and it would have all the way up to f of 2 times pi. All right. Basically what I would have is all of those numbers evaluated here. All right, all of those function values evaluated here. Okay, so the first point here is the value when x equals 0. The second point here is the value when x equals 0.001. The third point here is the value of x, or the value of the function when x equals 0.002. Okay, so to understanding that now, let's look at how we would plot something that's kind of complicated like this guy, right? So, in this case, what I have is functions that are multiplying each other, okay? And so the easiest way to think about this is let's try to generate these individual pieces one by one, all right? So first thing I'm going to do is I'm going to think of f1 of x as e to the x over 5, okay? And then I'm going to say this guy here is, all right, this guy is f2 of x equal to sine of 2x. And this guy, the third piece, I'm going to say is f3 of x equal to negative 2 cosine 2x. Okay, like that. So I basically have a combination of three functions that kind of come together to create the one big function. All right. So essentially what I would do is I'd say, well, first thing I got to do is evaluate f1 of x, okay, at all the points in my x vector. Okay. When I do that, let's say I did it and I created a vector f underscore 1 in MATLAB that was equal to, in this case, it would be exp of x over 5. Okay, that would be how I would create this. If x, the input, is a row vector, then f1 will also be a row vector. Okay, and the values in that row vector, if I were to look at them, will be exp of 0 divided by 5, and then the next value would be exp of 0.001 divided by 5. Okay, so this is the value when x equals 0. This is the value when x equals 0.001. Okay, so it's just going to continue on like that throughout the whole thing. All right, so I had a row vector coming in from my x, so I have a row vector coming out from my function. Okay, and I would do the same thing for f2. Okay, so I could do the same thing for f2 of x. In that case, I would get a function that looks like, a little bit different, right? In this case, I would get a function that looks like f underscore 2 equals sine of 2 times x. This 2 would, if I looked at it, right, if I plotted it or looked at it, just looked at the numbers, this guy would also be a row vector that would have sine of 2 times 0, and then the next entry would be sine of 2 times 0.001, okay, and so on and so forth, right? And then similarly with f3 of x, I would also get a row vector, right? And that row vector would have in it negative 2 times cosine 2x, okay? So I would get ultimately from that 3 row vectors, right? One for f1, one for f2, and one for f3. The question is, how do I put those row vectors together, okay? And that's a tricky question a little bit. All right, so let's look at this expression a little bit more carefully. So if f1, all right, so let's think of it this way. Let's say in MATLAB, the way I tried to put these guys together was I said I wanted to do it this way. F equals f underscore 1 times f underscore 2 plus f underscore 3. All right, if you look at the way these three functions are defined, this should seem like it makes sense, okay? There is a problem with it though. All right, let's start inside the parentheses first, right? Remember, we said all these guys are row vectors, okay? So if I think about what's going on inside the parentheses here, I'm going to have one row vector, which is going to have a bunch of numbers in it. All right, I'm going to make those numbers up for a second, all right, just to make this go faster. All right, and let's say it was very small. Let's say it just had the numbers 0, 1, and 2. Let's say that's what f2 equaled. All right, and then let's say f3 had the numbers, I don't know, 3, 4, and 5. Now, again, for the specific functions f1, f2, and f3, these would not be the numbers, right? But I just want to keep this simple. If I try to add those row vectors, that's perfectly fine to do. All right, adding those row vectors is perfectly fine. What I would find from that is I would get 0 plus 3 is 3. 1 plus 4 equals 5. 2 plus 5 is 7. Okay, those guys combine perfectly fine, and I get some combined row vector. Now, let's say f1 was also a 3-element vector that had 6, 7, 8, like that. okay? And you should see that, okay, F1, F2, and F3, if they were all created with the same x vector, they're all going to have the same number of elements. In other words, they're all going to have the same size. All right, so if I looked at trying to multiply these results, all right, 6, 7, 8 by 3, 5, and 7. All right, MATLAB is a matrix laboratory, right? That is its name. And so what it's going to try to do is it's going to try to multiply 6, 7, 8 by 3, 5, 7. So if you've taken linear algebra, you know that if I have 6, 7, 8 times 3, 5, 7, MATLAB just approaches these things like they are 1 by 3 matrices. Okay? This is an operation that you cannot do, right? We talked about matrix operations. Basically what you do is you take the first row here in this guy times the first column here. That's an operation that cannot be performed. Okay? But that's also not the operation you intended to have happen. What you want to have happen here is if this value here is the value of f1 at x equal to 0, and this value here is the value of f2 plus f3 at x equal to 0, well, what you want to have is you want to have 6 times 3 in your result. And you want to have 7 times 5 in your result. And you want to have 8 times 7 in your result. Well, that is something that you can do, but if you want to multiply each element in one vector by each element in the other vector, then what I have to do is I have to actually use something different, the Elementwise operation, which is done with a dot multiply. Okay? And in that case, this guy becomes, all right, if I do a dot multiply like that, I'll get, my first entry will be 6 times 3, or 18. My next one will be 7 times 5, or 35. And the last one will be 8 times 7, or 56. Okay? So what I ended up with is f is some function that is the same size as x. Okay? That makes perfect sense, right? Because I evaluated the function. We said this at the very beginning. I evaluate the function at the points in x, so I should get out something that is exactly the same size as x. Okay? So let's try to do this now in MATLAB. So let's bring up my code. All right? So here is some code that I wrote. Okay? So good function starts out with clear all. Make sure that all my variables are cleared up. All right? I say x equals 0 in steps of 0.001 to 2 times pi. Okay? So I've created my x vector. Then what I do is I create my f underscore 1. I create my f underscore 2. And I create my f underscore 3. And then I do the operations that I talked about here in the previous slide. So one thing I typically do before I make any final decisions about trying to plot anything, one thing I typically do is I usually check the sizes of things. All right, so what I'm going to do is I'm going to take these guys and I'm going to evaluate selection over here. So now everything's been created. So I'm going to look at the size of x. So this tells me that x is a row vector. It's a matrix with 1 row and 6,284 columns. Okay, so if I look at f underscore 1 and what its size is, same size. Same thing's true for f2. Same thing's true for f3. Okay, so once I know that, right, I got to be really careful about when I do operations like division or multiplication, when I am trying to operate individually on the elements of each vector like I had here, right? In other words, what I was trying to do is I was trying to have every element in this vector added to every element in this vector, or multiplied, sorry. So every element in this vector, so the 6 multiplied by the 3. The second element multiplied by the second element. The third element multiplied by the third element. Okay? So if that's what I want to have happen, I have to do the dot multiply like that. Okay? And so, to do that, one thing I'll always check is, sometimes I'll play around with these if I'm not sure. Once I know that they're both rows like this, then what I will do is I know it's perfectly okay for me to do the dot multiply, all right, or that's what I need to do. If I were to do, let's say, this operation without the dot multiply, let's see what happens, right? Incorrect dimensions of matrix multiplication. That's exactly what we talked about over here, right? Is that if I have 6, 7, 8 times 3, 5, 7, that's a matrix operation that cannot be performed. You can't have one row vector times another row vector. Doesn't make sense in linear algebra terms, all right? Now, what it's telling you here, it gives you a helpful hint that says, you know, if maybe what you're trying to do is element-wise multiplication, all right, which I am. So what I do is now evaluate selection. Oh, and it worked, all right. To check to see if it came out to be what I wanted it to be, I say, let's look at the size of, size of f. Now, f has the same size. Now, let's say for sake of argument, all right, that maybe you had defined one of these guys improperly, and maybe it was a row or a column vector. All right, so let's say this little operator here, I talked about it before, that turns a row vector into a column vector. So let's say I did that. Okay. Now, if I do that, I want to be careful about how I do it. Let me do that, not to that one. Let me do it to F1. Okay. All right. So what I'm going to do is take this. All right. And then I'm going to check the size of everything. Okay. F_1. This guy now has 6,284 rows and 1 column. All right. If I look at the size of F2 plus F3, all right, that has 1 row, 6,284 columns. Now, if I check that operation, all right, if I were to then try, if I had this, all right, 1, 2, 3, 4 times 1, 2, 3, 4. Let's say I did that operation, right? Now I have a different situation here, right? So let's say I do that, F1 times F2 plus F3, all right? Now it does something, and notice it actually did something pretty crazy. All right, so let's watch that. That operation can be performed, right? Again, if you know your linear algebra, right? I can do row times column and row times column. In this particular case, this guy's going to end up being a 4 by 4 matrix, okay? So let's look at this. What size did this guy become? That guy became a 6,284 matrix by 6,284. All right, I got to be really careful. If what I intended was to multiply elements one by one, I got to make sure that the vectors all have the same exact size. All right, you may think what I did here was arbitrary, but I guarantee you, if you're not careful, you'll end up making mistakes like this because you're not paying attention to how things have been created. All right, so now I got to make sure that everything is the right size, and then I can perform this operation. All right, now to create the plot is pretty straightforward. Let's run that. And there's my plot. All right. Now notice one thing I always do is I always include this figure 1 here. If I do that, it makes sure the plot always shows up directly for me. Okay.